I hope everybody got some Twizzlers if you wanted some. I brought Twizzlers. They're over there. Anybody wants them? Help yourself. I don't like them. So we are going to talk some more today about the first derivative and what it means about the graph. That's what we started talking about last time. The derivative and what it means when you look at the graph. So last time we discussed increasing versus decreasing, and this is related to the derivative, the sign of the derivative. So f is increasing when the derivative is positive, and it's decreasing when the derivative is negative, when f of x is less than 0, right? It's confusing. I'll just write the word. A typical function will be increasing sometimes and decreasing some other times. This one that I drew there, you could tell me intervals of x values where it's increasing versus where it's decreasing. In this case, I would say this, for this one right here, I would say it's increasing for x in the interval. Actually, there's two places where it's increasing, right? I'm just looking at where it's going up as we go left to right. That would be here and also here, right? So in terms of intervals of x values, that would be minus infinity to 2. That's this part over here. X values from negative infinity to x equals 2. And then also this part over here is 1, 2, 3, 4, 5. 5 to infinity, right? Everything greater than 5. 5 to infinity. And then it's decreasing in the middle there. So that's where it's increasing. And I will say decreasing. I'll write it over here. Decreasing for x in the interval from 2 to 5, right? And when we say these, we always are going to say them as open intervals because, right, for instance, this is from minus infinity up to 2 as an open interval. Right at 2 is this point right here. Specifically at x equals 2, the function is not increasing or decreasing there. So technically, where it's increasing is only up to but not including 2, and so on. It's always going to be open intervals for this increasing versus decreasing thing. All right? Any questions about that? It's pretty simple, in my opinion, if you know what you're looking for, to look at the picture and say, where is it increasing or decreasing? Give me intervals like that. All right? I would like to talk, what's more interesting is how do we do the same thing, answer the same question, but without looking at a picture? So just from, I will say, just algebraically, we can do the same thing. Algebraically, that is, using the equation, not looking at the graph. How can you do this? Oh, sorry about that. I'm going to turn the volume down. This is my life hack. I may be ruining it for people who want to use these later and don't try that to turn the volume back on. How do we do this without looking at the graph? Well, you can still identify these 2 points without looking at the graph, right? Those 2 points can be identified by finding when the derivative is 0. And you can do that just with the equation. You take the derivative, you set it equal to 0, and then solve for x. So first, to do this just algebraically, I'm going to say first, find the critical numbers. Remember, the critical numbers are where the derivative equals 0 and also where the derivative does not exist. For really nice functions, you don't even have to care about the does not exist part. That does come up if you have like a denominator or something. You have to check when the derivative does not exist. But anyway, first we're going to find the critical numbers. These are the places where the derivative is 0 or does not exist. For all values in between, the derivative either has to be positive or negative, and you can just check those. I'm going to say first find the critical numbers. This will become much clearer when we actually do an example in a moment, but I'm going to try and describe first. First find the critical numbers, and then plug in values in between to see where f prime is positive versus negative. All right? The critical numbers are the specific points when the derivative is 0 or does not exist. That means everywhere else, it's got to be either positive or negative. And we can check if it's positive or negative in this or that region by just plugging in specific numbers and see if they're positive or negative. All right, let's do an example. I'm going to do a few examples, actually. First is a, more or less easy example, and then we'll do a slightly harder one. How about f of x equals 3x to the 4 minus 4x cubed minus 12x squared plus 5. And I would like to say where it's increasing and decreasing. That is, intervals of x values, increasing on this interval, decreasing on this interval. That's what I want to do. All right. Like I said before, we begin by finding the critical numbers. That's where the derivative actually is 0 or does not exist. Although this being a polynomial, there's no opportunity for the derivative to not exist. So we should start by finding the derivative. Somebody want to shout it out for me? What's the derivative here?
12x cubed minus 12x squared minus 24x.
Yeah, great. That's the derivative. This is a simple derivative. And then, like I said, I'm going to set this equal to 0 to find the critical numbers. I think actually before I do that, I'm going to try and simplify as much as possible. You know me, I'm usually not really into simplifying things unless there's a good reason to. There is a good reason to in this problem. We're going to be using the derivative over and over again as we go on in the problem. So I'm going to simplify as much as I can. In this case, that would involve factoring. Ordinarily, a cubic is hard to factor, but this one is not so hard because there's no constant, like everything has an x in it. So I'm going to take out x of everything, and actually, you can also factor 12 out of everything. So I'm going to factor 12x out of everything, and what remains is x squared from the first part, and then minus another x, and then minus 2, right? And then you can factor that all the way. One of these, right? Anyone say what are the factors going to be? Somebody else want to shout out the factors?
X minus 2x plus 1.
Yes, thank you. X minus 2, x plus 1. By the way, thank you for desegregating the middle section here. It's the first time a female student has sat in the middle. Thank you for that. I don't know if anyone noticed. I notice these sorts of things. I forgot the x. 12x in the front, right? Like that. This is as simple as it's going to get, right? This is fully factored. So this is my f prime of x. I'm going to put this in a little box or something. We're going to be referring back to this formula several times. Anyway, let's find the critical numbers. Those are the places when the derivative does not exist or equals 0. So the critical numbers, there's two categories. One is f prime equals 0. So that would look like 12x times x minus 2 times x plus 1 equals 0. And this we can solve by, factoring. We already factored. So it's nicely set up. You just sort of break this out and set each part equals 0. Right? And so the first guy is x equals 0, and then I also get x equals 2, and I also get x equals negative 1. So these are 3 critical numbers. Remember, critical number means when the derivative is 0 or when the derivative does not exist. So we also should check f prime does not exist. But this just never happens in this case. The derivative is right here. There is no value of x when this does not exist. What I'm looking for is 0 in the denominator or something like that. But that can't happen in this formula. So f prime does not exist. I will just say not applicable, right? There are no values where the f prime does not exist in this example. What you're looking for in that step is something like 0 in the denominator, but that doesn't happen in this case. So we don't have to worry about that. Anyway, these are my only critical numbers then. I have 3 critical numbers, right? 0, minus 1, and 2. So my critical numbers are 0, negative 1, and 2. And remember what I said my strategy was going to be? I find the critical numbers, and then That means all the other values are where the derivative is either positive or negative. All the other numbers that are like in between these ones. And I'm just going to make a little chart here in which I mark off the critical numbers. And I'm putting them in order. If you mess up the order, then it'll confuse you. These are my special x values. And then I'm trying to determine f prime of x. It is 0 at those 3 points. That's why I care about those points, because those are the 3 points where the derivative is 0. And then at all other points, I want to know, is it positive or negative? And so what I'm going to do eventually is fill in this chart with like signs in between those zeros, either positives or negatives. I want to know, is it positive, negative, in between? All you got to do is just choose your favorite number, say between 0 and 2. Choose your favorite number between 0 and 2, plug it into the derivative, and see what you get. Is it positive or negative? All right? Whatever it is going to be that same sign all the way throughout this interval, because it can't be 0 any other place. So if it's positive somewhere in between, it has to be 0. It has to be positive between all points in this little range from 0 to 2. Anyway, what do you think? What's your favorite number between 0 and 2? 1. Yeah, you should choose a nice friendly number, as the kids call them these days. So in this interval here, I'm going to choose 1. So I'm going to do f prime of 1, all right? This is called a test point. So our strategy here is choose test points in each little interval. On this line, right? So I'm going to choose 1 between 0 and 2, 1 between the minus 1 and 0, and then also 1s on the ends. All right. Let's see what we got. F prime of 1. Okay, I've looked back on your paper to the formula for f prime. You should use the simplest one you can, although you could use any formula, like any of these here would be okay, because they're all equal to one another. But because I'm about to plug a value in, I'm going to use this one, especially, say, on the test when you don't have a calculator. I will just bring this on down here, put it there maybe. All right, I'm going to plug in 1 to that. I get 12 times 1, 1 minus 2, 1 plus 1, right? And then whatever that is, remember, I don't actually care if this is, I don't actually care what the number is. I care only if it's positive versus negative. So here's a little hack for doing this without using your calculator. This one's not so bad, but all I care about is positive versus negative, right? What I have here is 4 things multiplied together. This is positive times a positive times 1 minus 2 is negative, and then 1 plus 1 here is positive, right? I'm just going to think about positives versus negatives because I don't actually care what the answer is. I only care if it's positive or negative. And what is that? 3 positive times a negative is a negative. Yeah, the rule is like if there's an even number of negatives, then they all cancel out and you get a positive. If there's an odd number of negatives, you get a negative. Anyway, this is a negative, so I'm going to put a big old, that's a minus sign right there in this little range here. Because the value that I chose was in between 0 and 2, and apparently the derivative is negative in that range. All right, I'm just going to do that 3 more times. It's not so hard. How about, what's your favorite number bigger than 2? How about 3? There's no reason to choose anything else. Again, plugging into the formula in the box up there, it's going to be this time 12 times 3 minus 2 times 3 plus 1. And these, you could try to compute that number, but it's easier to just think in terms of positives or negatives. That's a positive, that's positive, that's positive, and that's positive. These are all positive, and so the product is positive, and so over here, the derivative is positive. All right? And we're just going to continue this. How about all the way on the far left? I'm going to choose minus 2, I guess, to the left of negative 1. So I do f prime of minus 2. That's 12 times minus 2 times minus 2 minus 2 times minus 2 plus 1. This is positive, negative, negative, negative. Those are 3 negatives, makes a negative. So I get a negative over here. And then finally, this is the worst step. I have to plug in like -1/2 in between -1 and 0. So let's plug in -1/2. F prime of -1/2, 12, -1/2, -1/2, -2, and -1/2, +1. This is positive, negative, negative, positive, right? -1/2 + 1 is positive. And so that's positive overall. So these are my signs. Come on. Minus, plus, minus, plus. All right? You'll find in many cases that the signs alternate. This is true generally of a polynomial which will fully factor like this with no double roots. That's always going to be the case. The signs will alternate. Although in every other case, you should not expect them to alternate. So the signs do not always alternate, but they do in the nicest examples. All right. We're pretty much done at this point. I said, the question I was trying to ask is, on which intervals is it increasing, and on which intervals is it decreasing? So the answer is, according to this chart, the pluses are increasing, the minuses are decreasing. So in conclusion, I say, I'm going to have to scroll back and forth. So f, the original function, is increasing on the intervals -1 to 0 and 2 to infinity. -1 to 0 and 2 to infinity. And the f is decreasing on the other intervals. -infinity to -1 and 0 to 2. All right. That's how we do them. This will take you, take you 10 minutes or so to do one of these problems. The individual steps are not all that difficult. Anybody got questions about that? This is how you say where the function is increasing versus decreasing. All right? I'm going to try another one that's a little more interesting. That was sort of an easy one. It still took us a long time to do, but not so difficult, really. How about, same question. Where is it increasing / decreasing? This time my function is f of x equals x squared minus 7 over x minus 4. How about that? We're going to try to do all the same steps. Remember, we began by finding the critical numbers. Those are the numbers you put on the chart. Then you plug values in between and see the pluses and the minuses. So to find the critical numbers, that's how we begin. We take the derivative here and then say when the derivative is 0 or derivative does not exist. When you think about the derivative here, what's my strategy going to be? Anybody feeling like using one of the rules? I feel like using one of the rules. What do you think? The quotient rule. Yeah, this is a fraction. The way to handle that is with the quotient rule. I hope you remember the quotient rule. It is the bottom times derivative of the top, which is 2x, minus the top, x squared minus 7, times derivative of the bottom, which is 1. All of this over the bottom squared. All right. That's my derivative. As before, I want to simplify this as much as possible. Like if this whole question was just find the derivative, and then I would leave it like that. That is the derivative. But for the sake of doing the rest of this problem, you're going to want this to be as simple as possible. What can we do to simplify? Well, one thing is, I would say don't multiply out on the bottom. That's already good. Usually in this type of problem, you want to factor things as much as you can. Now the top here, I hope you're not tempted to do this kind of thing. That is a bogus cancellation right there, because the x minus 4 up top is not factored out of everything. It's only on like the first half right here. If you want to cancel something, it has to be factored out of everything. Anybody have a suggestion about what we could do here? I would like to somehow, my goal at this point is to combine the top into like one thing. What I have is this piece minus this piece. I want to like actually subtract them. Any suggestions? I want to actually combine everything up there. see some people writing things, but they're not saying things to me. Somebody want to shout it out? Yeah, what do you think? Mm-hmm. Yeah, right. I'm going to distribute this 2x, maybe distribute the minus sign too, and then we can just sort of add everything up in the numerator, right? This, I hope you agree, this times 1 doesn't really make any difference. So yeah, let's do all of that distributing like he said. Up top, I'm going to get 2x squared minus 8x, and then minus x squared plus 7. That's distributing the minus sign there. Unfortunately, if you screw this part up, you're going to be screwed for the whole rest of the problem. So the moral of the story is, do it right. not very helpful comment, but yeah, it's true. I think it's like this: x squared minus 8x minus 7 over x minus 4 squared. And let's factor the top. I like to see everything factored out in this type of problem. That's the way you want to do it. So I factor the top. It's going to be x minus 7, x minus 1, right? Over x minus 4 squared. Okay, this is the simplest form that this is going to get, the derivative. I wanted all to be factored just so that it makes the plugging in at the end easier. When I go to plug those numbers in, I go like, this is positive, this is negative, that stuff. That is best to do when it's factored. Otherwise, you're going to have to use a calculator, which is fine in your own personal life, but on a test or whatever, I would expect you to do all of these without using a calculator. All right, that's my derivative. Now I need to say when the derivative equals 0, and also when the derivative does not exist. And in this case, you actually do need to consider both parts. Let's try the derivative equaling 0 first. I set that whole thing equal to 0. Right? How would you solve this equaling 0? Well, when I have a fraction on the left side, I would do like a cross multiply the denominator of the fraction. So this denominator here multiplies over to the right side, and it will just say this stuff: x minus 7, x minus 1 equals 0 times x minus 4 squared. But that is just 0 on the right side. 0 times something is always 0. So it's just x minus 7, x minus 1 equals 0. And lucky for us, this is already factored, so you can just say immediately x equals 7 and x equals 1 are my critical numbers where the derivative is 0. All right? So those two numbers are going to go on my chart. We also have to check when the derivative does not exist, which that actually is relevant in this problem. You look at the derivative formula, which is in the box there, and you ask, is it possible that this thing could fail to exist for any values of x? That would be, what you're looking for is 0 in the denominator. What value of x makes a 0 in the denominator here? Show me the fingers if you want. Yeah, 4, right? East Coast. It's too many. Did I do it the wrong way? Do it this way. 4 is the answer, yeah. So if you wanted to write out some steps, really what you're looking for is the denominator equaling 0, which would be x minus 4 squared equals 0. And this, when you I guess you could square root on both sides. X equals 4, however you want to come up with that. But this is, in a harder problem, you might have to actually do some work here, although it was all factored already for us, so no problem. All right, these are my 3 critical numbers. I get this, this, and this, right? 1, 4, and 7. So I'm going to make my little chart here with my critical numbers. 1, 4, and 7. And then we're going to choose values in between, just like we did before, and plug them into the derivative formula, which I'll copy down there so we can still see it. Right? That's the derivative formula. So let's choose your favorite values in between these, plug them into the formula in the box. Far on the left, all the way on the left, let's choose 0. I always choose 0 when that's an option. So leftmost value to choose. Oh, anyway, sorry, I'm going to write down f prime down here. We have 0 there. I'm going to write this. dne in the middle and a 0 there, right? These are the values of the derivative. 1 and 7 were places where the derivative was 0, and 4 is a place where the derivative does not exist. Okay, anyway, plug in values in between. When I plug in all the way on the left side, I'm going to use x equals 0. So I go f prime of 0. This is going to be 0 minus 7, 0 minus 1 over 0 minus 4 squared. Here's a little tip. No matter what, the denominator, in this example, the denominator is always going to be positive, right? Because it's a thing squared. So you can just remember that, I guess. What is this? This is a that's negative times a negative divided by a positive, all right? And so overall, that one is positive. Positive. Again, you're looking for sort of, is there an even or an odd number of negatives when you multiply it all together? All right? How about between 1 and 4? What should we choose? 2, yeah. Your favorite number between 1 and 4. You don't have to choose like the number exactly in the middle, which is inconvenient in this case. That'll be 2.5, which I don't want to get into that. 2, f prime of 2 is 2 minus 7, 2 minus 1 over, and I just say something squared, is always going to be positive down there. This is negative times positive over a positive, which is negative. So that region is negative. This is pretty, routine. It's a little tedious. You just got to plug all these numbers in. How about between 4 and 7? I'm going to use 5. F prime of 5 is 5 minus 7, 5 minus 1 over something squared. This is negative, positive over positive. So that is also negative. All right, here's an example where the signs do not alternate as you go across. You should not always expect them to alternate. Sometimes they just don't. And then to the right of 7. 7 is our rightmost value there. On the right of 7, let's choose 8, I guess. F prime of 8 is 8 minus 7, 8 minus 1 over something squared. This is positive, positive over positive. All positive, positive, like so. All right. I hope I did it right. Any thoughts about that? Just a lot of, it takes you a while to do this, but every step is pretty simple on its own. All right, and then what's my final answer? I said the question, remember, was tell me where it's increasing and decreasing. So I'm going to say it's increasing on wherever you see pluses, the interval minus infinity to 1, and the interval 7 to infinity. And it's decreasing otherwise. That would be 1 to 4 and 4 to 7. You might be tempted to say, can I just say like from 1 to 7 it's decreasing? That's not technically correct because it is not decreasing right at the number 4. It's decreasing between 1 and 4, but not at 1, and also not at 4. And it's decreasing between 4 and 7, but not at 4. All right, that's how we do it. I don't know if you're wondering, like, what does this even look like? How could it be that it decreases and then does not exist and then decreases again? This is because this function, the original function, has an asymptote at 4. So it looks like this is 4. This function looks something like this. So it has this. It increases up to this point and then decreases until 4. There's nothing at 4. But then after 4, it's still decreasing, and then it starts to increase again. So that's what this function looks, something like that. All right. Any thoughts about that one? These are the kinds of examples that you're going to do on the next homework assignment. Not the one for this week, for next week. All right. This picture, actually, looking at the picture that I just drew, you may gather that this increasing, decreasing business also has a lot to do with the relative extrema. Remember the relative minimum and maximum points? Like in this picture, they would be here and here. In fact, they would be, these numbers, 1 and 7, right? That's where these points are. Basically, the same procedure that we've just been following is sufficient to find where those kinds of points are, the minimum and the maximum points. And not only that, but you can tell those points in this example, they're at 1 and 7. And also, by looking at the chart, you can tell the difference between a minimum and a maximum point, the local minimum and the local maximum. So all of this is sort of summarized in a theorem. So I can say we can use that same chart with the pluses and the minuses to identify local minimum and maximum points. Local min and maxes. And there's sort of a big sounding name for this concept, and it's called, I'll go to the next page here. I'll write this as a theorem. It's called the first derivative test. It's called the first derivative test because you use the first derivative to do it. There's also a second derivative test which uses the second derivative, the derivative of the derivative. But this is the first derivative test. The sort of picture you should have in your mind is, you have some kind of function like this, and it has some local minimum and maximum points. Now that function that I just drew, it increases over here, it decreases in the middle, and then it increases again, right? That's increasing, decreasing just means is it going up or down as you go to the right. The first derivative test, it says, let C be a critical number. Of f of x, and assume that f is continuous at C. This means, for example, this rules out the asymptote case. The function actually has to be continuous at the point for this to be true, but this is usually going to be the case in our examples. Then it says, I'm going to write a lot of words here that are the meaning is very intuitive, although there's not a very short way to say it. If f goes from increasing to decreasing at, I'll say near C, then C is a local, I'm going to fill in the blank here, local minimum or local maximum. You can see on the picture here, like this point right here, near this point, it goes from increasing to decreasing. That means that point must be a maximum, right? It increases, it goes up until it gets to that point, and then it goes back down again. That means this point must be like the top of the hill. It has to be a local maximum. So if f goes from increasing to decreasing near C, then C is a local maximum, all right? Why this is good is you can tell this just by looking at the chart, where those pluses and minuses go. If it goes from a minus then to a plus, it means that point is a maximum. And other way around, if f goes from decreasing to increasing near C, then C is a local minimum, right? On this picture, that's what happens right here. It's decreasing, and then you hit that point, and then it increases again. That means that point must be like the bottom of the hill, so it's a local minimum. And there's one other case. It could go increasing and then increasing again, or it could go decreasing and then decreasing again. And in that case, the point is not a local minimum or maximum. So if f goes increasing to increasing or decreasing to decreasing, that is, it doesn't switch, it just keeps doing the same thing, then that means your point is just like in the middle. Like it increases up to your point and then continues to increase some more. That means that point is not at the top or the bottom of the hill. It's nothing. It's not a local maximum or minimum. So if f goes increasing to increasing or decreasing to decreasing, then C is not a local max or right? This is called, all of these words together are called the first derivative test. It is how you can find where the local maximum and minimum values are. You make that big chart, and then you just look how the signs are changing. If it goes plus to minus, that's a maximum. If it goes minus to plus, that's a minimum. And if it's plus to plus or minus to minus, that's neither. All right? So, for example, the previous example we just did, remember, eventually we got down to this chart here, 1, 4, 7, and the signs went, there was a d and e in the middle for the derivative. The signs went plus, minus, minus, plus, right? So, according to the first derivative test, you can just look at the chart here and say which of these points is a maximum, local maximum or a minimum. So, x equal 1 is a local maximum. That's because when you look on the chart near x equal 1, it goes from plus to minus. That's the rule. If it goes increasing and then decreasing, that means it's a local maximum. So the reason it's a local max is because it goes from plus to minus near 1 on the chart. All right? 4 on the chart goes minus to minus, so that means 4 is not a maximum or a minimum. Furthermore, the function doesn't even exist at 4, so the 4 is not anything, really. But 7 is, x equals 7, is a local minimum this time, because it goes minus to plus. And this rule, the first derivative test, I guess you just have to memorize, although I think it's pretty easy to remember. If it goes plus to minus, that means it goes up and then back down again, which means your point is a maximum. All right, and I will just say parenthetically, x equal 4 is not a minimum or a maximum, right? In fact, in this particular example, x equal 4 is not even part of the domain of the function, right? It was an asymptote. All right, this is called the first derivative test to identify where the local extrema are. All right? Any thoughts about that? I got one for you all to try. See if you can. For this function, f of x equals 3x to the 4 plus 4x to the third plus 1. I would like you to find intervals where it's positive or negative. Sorry, where it's increasing or decreasing. And also find x values for the local, I'll use a fancy word, the local extrema. That means minimum and maximum points. All right? These are two different questions, but they both can be answered directly from that chart. So basically, the bulk of this is making the chart, and then you just read these two answers straight off the chart at the end. All right? See what you think. got more Twizzlers. Nobody seems to want them. You guys are into red vines, I guess, right? I don't like either. Let's try this out. It looked like most people were doing great with this. We should start by doing the derivative. I get 12x squared plus 12x. What? No, 12x cubed plus 12x squared, right? And then I'm going to factor 12x squared out, and what remains is x plus 1. And so my critical numbers, when the derivative equals 0, is x equals 0 and x equal minus 1, right? Here the 0 is kind of a repeated root because of this, x squared thing here. F prime does not exist. We don't really need to worry about because there are no denominators to check or anything like that. So 0 and negative 1 are the only points that need to go on your chart. I'll put them on here. These are my x values. This is my f prime of x will be 0 at those 2 points. And then I choose values in between to plug in. On the left side, let's choose, so this is my derivative. On the left side, let's pick f prime of minus 2. That would be 12 times minus 2 squared times minus 2 plus 1. This is positive, positive, and negative, so it's negative over there. I hope that's what you got. In between minus 1 and 0, I guess I have to use negative a half. So I go f prime of minus a half. 12 times minus a half squared minus a half plus 1. This is positive. Positive because it's a square. And then minus a half plus 1 is positive, right? That's positive a half. So positive here. And then finally, to the right of 0, I will use 1. So this will be f prime of 1. 12 times 1 squared times 1 plus 1. These are all positive. So it's positive over there. All right. Remember I said when you have a polynomial with no repeated roots, you should expect the signs to alternate. But this one had this repeated root here, x squared, which is why this doesn't alternate. Okay, that's the chart. I hope you got something like that. Anyway, to answer the specific questions, the first question was, give me intervals where it's increasing or decreasing. So I say increasing is where the positives are. So it's increasing on the interval minus 1 to 0 and also 0 to infinity. And it's decreasing on the other one, minus infinity to minus 1. Right? Those are the intervals of x values. And then how about extrema? You look on the chart and you see where does it go from minus to plus or plus to minus. Actually, it never goes from plus to minus as you look across the chart from left to right. It goes minus to plus right here. So this one, I'm going to say x equal minus 1 is a local. Minus to plus means down and then back up, so it must be a minimum. X equal minus 1 is a local minimum. All right? If you want, you could say x equals 0 is not anything. But, I mean, if I ask you, tell me where the local minimum and maximum points are, that's my answer. X equal minus 1, it's a local minimum. There is no other local extrema. All right? Any questions about that? I hope you got it. Excellent. Great. Everything that I've said so far has been about the first derivative, right? We are only using the derivative, f prime. Remember, there is such a thing as the second derivative, f double prime. That is the derivative of the derivative. It turns out the derivative of the derivative, f double prime, is also meaningful, or I'll say visible graphically. Right? When your friends ask you at dinner time, what does the derivative mean on the graph? It means, is it like going up or going down? That's what the derivative means. Increasing versus decreasing. But the second derivative also has meaning when you're looking on a graph. This is a little more complicated, but we can handle it. Remember, if f prime is positive, means the original function f is increasing, right? That's just what the first derivative means. But I put that in brackets. That's just like a review. Everybody already knows that. What I'm trying to talk about now, though, is the second derivative, f double prime. But if you believe this line here, just write this again, but using the derivative of the derivative instead. What this means is that f double prime is positive, means f prime is increasing. F prime is increasing. What that means is as you go left to right on the picture, the slope is increasing. That is, it's getting steeper as you go from left to right. The slope is becoming bigger and bigger, all right? F prime is increasing. What that means in more ordinary language, the slope is becoming bigger and bigger as you move left to right on the picture. Right? What does that look like on a graph? It looks something like this. This is an example where as you move to the right, the slope is becoming bigger and bigger, steeper and steeper, right? Now this is slightly confusing because it might look like if on this side, as I move to the right, it starts off quite steep and then gets less steep as I move to the right. But that actually also counts as increasing in slope because here the slope is super negative and it becomes less negative, which counts as the slope getting bigger and bigger, all right? This is a technicality, but both sides of this picture have the property that the slope is increasing as you move from the left to the right. Either the slope is super negative and becoming less negative, or on the right side, the slope is already positive, but it's getting more and more positive as you go to the right. All right. So this is the classic picture of a function. So when you see that kind of shape, this has f double prime greater than 0. This is what it looks like when the second derivative is positive. And there's a name for that kind of shape. It's called concave up. And it means you have, well, I'll draw the other alternative. Let me just say, other situations which can look like concave up would have two other. Maybe it's just kind of flat on the left side, but still doing that sort of increasing slope on one side. Or maybe it just has like the other half. Any of these pictures here, they are all called concave up, this general shape. It is a shape in which the slopes are increasing as you move from the left to the right. By increasing, I mean either really getting bigger or getting less negative. That's the case in this one. That counts as increasing, getting less negative or getting more positive. All right? All of those shapes count as concave up. The opposite is that the slope is getting smaller. It could be super positive and becoming less positive, or it could be negative and becoming more negative. That picture would look like this. Right? As you move from the left to the right, here the slopes are positive, but they are becoming less so positive. And over here the slopes are already negative and becoming even more negative. This shape is called concave down. It could also look like, so other kinds of shapes that are also concave down would be maybe just like half of that picture, something like that, or maybe something like that. These are all concave down. So for these, f double prime is less than 0, and it's called concave down. All right? That's the terminology. And concave up versus down is fairly simple. I mean, I always think of it in terms of like the fingers, right? This is up. This is down. This is concave up. This shape, this is concave down. Concave up is concave up is like the smiley, right? And concave down is the frowny. Is this way, a frowny, right? And you just have to remember that concave up, this one, means that the f double prime is positive. Positive means smiley, right? And this one is the one where the f double prime is negative, meaning the frowny shape, okay? This is how you identify concave up versus down on a picture. And this is the graphical meaning of the second derivative. So the first derivative is the curve actually going up or down? That's the first derivative. The second derivative is this sort of smiley versus frowny shape, all right? Does it have the smiley shape or the frowny shape? This is called the concavity of the graph, all right? Let's just look at a picture and see if we can identify, as usual, a typical function is like sometimes concave up and sometimes concave down. It's like sometimes the smiley, sometimes the frowny. A simple example would be like a typical cubic equation looks something like that. Come on now. Something like this, right? You can see part of it is the frowny and part of it is the smiley, right? And there's some point, I suppose, right in the middle somewhere, maybe around here, where it switches from being the frowny to the smiley, all right? But I would say this region right there, maybe till around there somewhere, versus this region over here, right? This part is concave down, because that's the frowny shape, and this part over here is concave up, because that's the smiley shape, all right? And that point right in the middle is neither. At that specific point in the middle, it is not concave up or concave down. There's a name for that. This is called an inflection point. This is a point at which the concavity changes from being up to down. So right at that point, it is neither. In fact, in this case, the second derivative will equal 0. Remember, the concavity is determined by the second derivative. Is it positive versus negative? On this picture, to the left of that dot, it's negative because the concave it's concave down. To the right of that dot, it's positive, and right at the dot, the concavity, or the second derivative, must be 0. All right? Let's do a more complicated, more interesting picture here. How about, I'm going to try to make these points the way I want them. Like that, all right? I would like to give me intervals where it's concave up versus concave down. That's what I want. Intervals for concavity. You want to look at that picture and identify where is it a smiley shape versus where is it a frowny shape. Sometimes you don't get the full smile. You only get like half of the smiley shape or the frowny shape. Anyway. For the concave up, I'm looking for the smileys, right? I would say there's definitely a smiley region over here, right? I see that smiley shape there. You'll have to kind of judge exactly how far over does the smiley shape go. Does anybody see another smiley region? Like I said, sometimes you don't get the full smile. Sometimes you only get half of the smile. You see that?
After 2 and
Yeah,
3.
yeah, like between 2 and 3, it has this kind of at least half of the smiley shape, all right? And I think those are the only places on this graph where you get the smiley shape. I think everywhere else is going to be the frowning shape. The frowning shape, maybe I'll put those in green here. I see the frowny, sort of a half frowny right there, and then a full frowny over there, right? These are the concave up versus concave down regions. So writing those as intervals, I would say it's concave up over here. That is everything to the left of x equals 1. So from x equal minus infinity up to 1. Concave up. And also this bit right here. And it looks like right there, I tried to draw the picture so that right there is where it switches from being up to down. So the other concave up region is here, 2 to 3. Those are the upsies, and the downsies are the other parts. I guess from 1 to 2, this one, and then over here, everything greater than 3. So concave down will be 1 to 2 and 3 to infinity. All right, this is the concavity. I would like to contrast this with increasing versus decreasing. These are really two completely different concepts. You can also, we can also do, looking at this same example, I will say note. What are the increasing, decreasing intervals? It's increasing, that is everywhere it's going up. I guess from here all the way to there, it's increasing, right? And that's it. So the increasing, and maybe this point is where, I tried to draw this so that the slope is 0 there. So technically it's increasing here from 0 to 2 and 2 to 4, right? That's this region and this region. It's increasing, that is going up from left to right. And then it's decreasing over here, minus infinity to 0, and also 4 to infinity. These intervals are really completely different from the concavity intervals, right? There's no simple relationship between the two. So they are really two completely different concepts. They mean different things, right? Increasing, decreasing is just, is it going up or is it going down? The concavity is about the shape, the curvaceousness of the shape. Is it the smiley shape or the frowning shape? All right. All right, and I was going to say, what are there any inflection points here? I think there are. Remember, inflection point means it's one of the points where the derivative switches from being positive to negative or negative to positive, or the concavity switches. And that would happen like every time these frownies and smileys bump up against each other. So the inflection points, if I were to mark them with dots, would be here, here, and here, right? Those are where the concavity switches. So I'll just write that in here. Inflection points at x equals 1, 2, and 3 on this picture. That's where it switches from being smiley to frowny, or frowny to smiley, called an inflection point. They are similar to the critical numbers, but critical numbers are about the first derivative. The inflection points are about the second derivative. All right. Inflection points, you can always eyeball them on a picture. They are just like the points in between, sort of in between the bumpity bumps. If I have something like that, where are the inflection points? There's one here, because I see smiley followed by frowny. There's one around here. There's one somewhere like that, and one in there somewhere. Right? Those are the inflection points on this picture. Everywhere it switches from being a smiley to a frowny, or vice versa. All right, the inflection points. Some people, sometimes you hear people use the word inflection point in the real world to just mean like when something changes. Mathematically, it is about when the concavity changes, but it's a specific kind of change in the function. All right, any questions about that? Pictures? Let's try and do the same thing, but algebraically. That is, looking at an equation, not looking at the picture. Can we identify intervals of the concavity using the formula, not by looking at the picture? All right? The process is almost exactly like the increasing, decreasing thing, only you use the second derivative instead of the first derivative, right? The increasing, decreasing is about the sign of the first derivative. So I'm going to say we do the same procedure as increasing/decreasing, but we use f double prime instead of f prime. Because f prime tells you the increasing, decreasing. F double prime tells you the concave up versus concave down. So do the whole same thing. Set the thing equal to 0. Make the chart. Plug in points in between. Let's try it. I thought we'd just revisit the first example we talked about today. It seems so long ago, doesn't it? 3x to the 4 minus 4x to the 3 minus 12x squared plus 5. All right? And your job is find intervals where it's concave up versus down. All right? Like I said, we're going to do the same procedure, but use the second derivative instead of the first derivative. So my first step will be immediately find the second derivative. Now, you can't find the second derivative all at once. The only way to do it is take the derivative first, and then take the derivative again. So f prime of x is 12x cubed minus 12x squared minus 24x. Remember that guy? And then take the derivative again, right? I don't care about the first derivative at all in this problem. I care about the second derivative. So this will be 36x squared minus 24x minus 24, right? Did I go all right? Somebody has a puzzled look on their face. That's okay. What should we do from here? Maybe try and factor this. I mean, I always try and simplify as much as we can. Here, you could factor 12 out of all of that. What remains will be 3x squared minus 2x minus 2, right? And then try to factor that part that's left over. Unfortunately, that part there doesn't factor in ordinary numbers. Well, what do we do in that case? If it doesn't factor, I still want to find the, I expect to get 2 values for x, right? If it doesn't factor, the best you can do is use the quadratic formula, which usually we don't like to do, but in this case, it's the only way we're going to do this. So first, anyway, this is the most simple form of the derivative. It doesn't factor anymore. Sorry, the second derivative is what I'm talking about. Anyway, I'm going to set the second derivative equal to 0. It'll say 12, 3x squared minus 2x minus 2 equals 0. I can get rid of the 12. It's not relevant. It's just 3x squared minus 2x minus 2 equals 0. And here, I need to use the quadratic formula because, like I said, this doesn't factor nicely. I hope you remember your quadratic formula. Anybody remember it? I like asking rooms full of people to say the quadratic formula. They just sort of mumble a lot, and then everybody says all over 2a. Everybody knows that part. That's the end. It's minus. I'll just write the formula for now. Minus b plus or minus the square root of b squared minus 4ac all over 2a. Right? I hope that you know the quadratic formula. One of my teachers in middle school sang the quadratic formula song to the tune of the Yellow Submarine. I'm not going to get into that. There are songs for that if you require songs. Anyway, this is going to be 2 plus or minus square root. Negative 2 squared is 4 minus 4 times a, which is 3, times c, which is negative 2. All over 2 times 3. That would be 2 plus or minus square root. 4 minus... I guess that's going to be a plus. 4 times 3 times 2 is 24, right? Over 6. So this is 2 plus or minus the square root of 28 over 6. And now it's clear why you can't factor, because that root 28 is not a nice number. I plugged this into my calculator. You plug it, if you're going to plug this into your calculator, you do it once with the plus. Again, with the minus, you get 2 different answers. They were negative, with the minus, you get negative 0.548, and with the plus, you get 1.215, right? Anyway, remember what we were doing here? We're trying to find where the second derivative is positive and negative. We found these numbers with the intention of putting them on the chart, right? These are kind of like the critical numbers, although they're not critical numbers in this context. They are coming from the second derivative, so really they are inflection points. Anyway, I make my chart of the second derivative this time, and I mark those two values, negative 0.548 and positive 1.215. Those are two numbers where the second derivative is 0. It is important that you know what those numbers are. Like, you actually do have to put that into your calculator because you need to, my next step will be to choose values that are smaller and greater. And you have to know what those numbers are in order to make sure you're picking values in the right regions. Anyway, let's do it. What do you want to use? What's your favorite number on the left side? -1, yeah. And I'm plugging into the second derivative, which is, here's scroll up here, that thing in the box here, right? This is what I'm plugging into, all the way down here. So I get 12, 3 times -1 squared minus 2 times -1 minus 2. Unfortunately, I can't do my normal trick about negative times a negative times a negative, whatever. Because inside the parentheses there, those are actually added up. They're not multiplied together. So you really do have to compute the number, although it's not terribly difficult. -1 squared is +1, so this is going to be a 3, and then a +2, and then a -2. This is 12 times 3, which is a positive times a positive, so that's positive on the left side. All right? It's still, you don't actually care what the number is, you just care if it's positive or negative. Okay, in the middle region, I'm going to choose 0, right? That's my favorite number to plug in all situations. In the middle region, I use 0. Again, plug into the formula in the box. 12. 3 times 0 squared minus 2 times 0 minus 2. This is 12 times -2, which is negative. Right? And then on the right side, I suppose we should use 2. It's bigger than 1.215. So f double prime of 2 is, in the box, 12. 3 times 2 squared minus 2 times 2 minus 2. This is 12 times, 3 times 2 squared is 12 again, minus 4 minus 2. That's positive times a positive. So this is positive also. Signs alternate, which is not a surprise because this was a polynomial with no repeated roots. Okay, we're pretty much done at this point. My final answer should be intervals. Where is it concave up versus concave down? You just look at the signs here. So my final answer is it's concave up on the interval minus infinity to that number, negative 0.548, and also concave up on the interval 1.215 to infinity. And it's concave down. Oh, come on, buddy. Concave down on the one in the middle, right? Minus 0.548 to 1.215. Ah! I hit my page up button. There you go. This is my final answer based on the chart there. All right. That's how we find concavity intervals without looking at the graph. Unfortunately, we had to use the quadratic formula. You don't always have to use the quadratic formula. If you're lucky, the second derivative will factor, and then you won't need it. All right, I think that'll do it for today. See you all next time. Take a Twizzler on your way out. I got enough.